Okay. Hi, thank you for coming. My name is Mario Fusco. I work for Red Hat, and I'm here to speak about virtual threads. Actually, this talk is supposed to be the continuation of the talk that I gave last year. Who was here last year at my talk? Okay, some of you. Okay, of course, it's not necessary to have seen my talk to understand this, but in reality, yeah, I'm talking about virtual threads, but be warned that this is not an introductory talk about virtual threads. I'm giving for granting that you know what they are and how they work, more or less. But of course, if you have questions, interrupt me. I just wanted to show you the experiment that I did with this technology in the latest month to try to push it at the boundaries and see how it behaves. Okay, so I'm hoping it will be interesting to see my experience with this. Okay, but just a quick recap. So virtual threads are the idea of virtual thread is getting rid of the one-to-one relationship between Java threads and the threads provided by the underlying operating system. So the same with the same carrier, the same native thread can be multiplexed on multiple virtual thread, can be used by multiple virtual thread, and a virtual thread can be then mounted and unmounted by from the native thread that is called courier in this case. And this happens when it performs a blocking operation, because you don't want to block a native thread, which is a scarce resource, but it's okay to block a virtual thread because it's very, very cheap. And then what happens is that when a virtual thread performs a blocking operation, that virtual thread is unmounted from the carrier, so it gives space from another virtual thread to make some progress on the same carrier thread. And then when the blocking operation finishes, the virtual thread is ready to be mounted on a carrier which is not necessarily the same where it was unmounted, okay? And this carrier are a specific fork join pool that is provided by the Java virtual machine out of the box, and you cannot change it, or sort of course I've tried to change it, and I will demonstrate what happens if you try to in one of my examples. So in essence, what virtual threads are really good for is just waiting without wasting a resource. That's the thing, and this is because they are very lightweight. The metadata that they take is very, very small, just a few hundred bytes. The stack is not pre-allocated. They don't take one megs or more of stack like it happens with native threads, but the stacks grow as you need it. And the other important thing is that the context switch is much faster. It typically couple of order of magnitude faster than what happens with native thread, just because with native thread they are actually kernel threads, so the context switch happens in the kernel space, while in this case virtual threads are pure Java objects, so the context switch just happened in the user space. Okay, so these are all the cool things that virtual threads are and can do, and so everybody loves it, and let's start using virtual threads everywhere, right? And yeah, in reality, it's not that simple. Virtual threads are a tool, and the purpose of this talk is also showing their limitation and what they are good for and what they are not so good for, okay? So in reality, virtual threads are not so good for CPU-bound tasks. First of all, because there's a problem with fairness, because they are not preemptive. And there could be also some problem in performance problem introduced by the virtual thread scheduler. The other problem is that you cannot just use virtual thread everywhere for now, just because there could be a few frameworks and tools that are not virtual thread readed. So for instance, they have some synchronized block, and if they do a blocking operation in that synchronized block, the virtual thread remains pinned to the carrier thread, meaning that it cannot be unmounted, and in that case, you are not only blocking the virtual thread, but also its carrier, which is something that, of course, you don't want. And there is also a problem with the tools using ThreadLocals, and I will show you why. So yes, what Brian Gates said this morning is true. Virtual thread, the ThreadLocal works perfectly with virtual thread, but the problem is exactly there, and I will show you why. And the latest thing I mentioned in this that the carrier pool is not customizable, but this is also for a very good reason, and I will try to demonstrate why. Okay, so the first problem that I mentioned is that the lack of fairness, the lack of preemptiveness, which leads to also a lack of fairness. What this means is that simply when you use native thread, the native thread can be interrupted, and the machine, the CPU, the core can be allocated to a different thread. With the virtual thread, this cannot happen. So if or actually it happens implicitly if you do a blocking operation, but if your task is entirely CPU bound, you don't have any blocking operation, and then the virtual thread cannot be blocked, will continue its execution till the end. So just to demonstrate in practice what this means, I have this very simple application. This this is quite a common pattern that I will use throughout my example. I have this flag to run the same example using either native or virtual thread. And what happens here, just to make things clear, is that when I use a virtual thread, I consume the task with this method. So the task is executed on a virtual thread, otherwise is executed on a native thread executor. Okay, that's all. This is what happens when I flip this boolean. Okay, so now in this first run, I will run this thing with native threads. What this thing is doing is just launching. Okay, I have 8 core on my machine, so basically this is executing the same task on 64 different threads, and this is a purely CPU bound task, meaning that what I'm doing is simply counting from 0 to 10 millions big integer and doing some conversion to make this task even a little more CPU intensive. This is totally fictional. It's just a CPU bound task without any blocking operation, right? So let's try to run this with the executor that I create here with native threads then, and let's see what happens. So it will run this thing 64 times in parallel. At the end of the execution, I just gather and print some statistic here. So you can see, I have the 64 result coming from the 64 different thread. And what I do, I print the result that is equals for all, but I also print how long it takes in milliseconds. So you can see that the duration is more or less evenly distributed, maybe around a Gaussian curve. Okay, and you see I also print the thread that takes less time, 1.6 seconds. The one that took the most took 3.4 seconds, and the average is 2.8. Okay, so try to remember this number, and let's rerun this experiment again by flipping this boolean and run it again on virtual threads. Again, please interrupt me if you have question. Okay, see what happens here. Okay, the minimum duration is a lot less. It's just before it was 1.6 seconds, and now it's only 458 milliseconds. Right? What's happening here? it's happening what I'm saying. I have a 8-core machine, so the first 8 virtual thread take the CPU. So see the duration of the first 8 thing. They take the CPU, they continue till the end without leaving the CPU, and not giving room to the other thread to do anything. And then when they terminated, you have the other 8 thread. You see this gap between the number 7 and the number 8, and then you see the same gap between the number 15 and the number 16, just because of this reason. The virtual thread goes till the end of the task. It's not fair. It's not leaving space to the other thread to do its job, right? And yeah, of course, this means that you don't have fairness. So this is why I don't suggest you to run this thing with virtual thread. But in reality, if you are only interested in throughput, this is also interesting. If you remember, the average time before was 2.8 seconds. Now I'm below the 2 seconds. And this is simply because fairness has a cost, right? So if you are just interested in pure throughput, probably this could be a strategy. It's not fair, but you do more work in this way because you don't have any thread switch. You are not fair, and this of course improve the average throughput. Okay, so again, I have a few examples like this. Please feel free to interrupt me if something is not clear. Okay, so as I said, I tried to describe how virtual thread work. They are actually continuation. They can be mounted and unmounted, so they can be interrupted. And then the good thing of a continuation is that they can restart from the point where they have been interrupted. Then there is a scheduler, of course, mounting and unmounting this virtual thread from the carrier, okay? But also, of course, all this machinery has a cost. So I have a second example. This time is a proper benchmark made with JMH. I run this with 100 parallel thread that can be, this is a parametric benchmark, so I run this thing twice with virtual thread and with native thread. And what this thing does, well, it's very similar to the one before. The only thing that this does is consuming 100 CPU cycle. This is a facility that is provided by the benchmarking framework by JMH to say, okay, in this point, consume 100 cycle, which is this consume CPU is, you should think about it as the actual work made by the thread, okay? So let's try to run this and see what happens. So I don't know if you know JMH as a benchmarking tool. Well, not many, but what JMH does is it run this method.net benchmark for a few times. I said 5,000 times here as a warm-up, and then it runs it for real 10,000 more times in my case, and I'm only collecting the data for that cases, okay? And see what happens here. So when it uses virtual thread, it takes almost 100 microseconds, 99 microseconds to perform a single operation, okay? And when I'm using native thread, it takes only 38 microseconds to perform the same operation. Okay, so why is that? Because as I said, there is a cost in all the virtual thread machinery. Okay, so in this, I profiled this and created a flame graph for both execution. And what I'm evidencing here is that method that I mentioned it before, that consume the CPU, because it's the method that does the actual work. the whole thing around is the threading machinery to run the thread in parallel, but the actual work is done by that method. This is the native thread execution, and the actual work is happens in almost 22% of time, if you read there, okay? And if you do the same exercise with virtual thread, the actual work is made only the 2% of time this time. All the things around is the machinery to coordinate the virtual thread, okay? Of course, this benchmark is made on purpose to exaggerate the problem. In reality, you have some long running task, and in reality, you want virtual threads, especially if you perform blocking operation, as I said. So the time consumed in reality, but by your thread is probably order of magnitude bigger than this stuff, so you don't see them in reality. But I just wanted to demonstrate that the virtual thread machinery, of course, doesn't come for free. There's a cost, and you probably want to consider it. Okay? Yes. Question? No, the problem is not the countdown ledge. The problem is that the line that you see in purple, that I put in purple there, is the line that is mounting, that is signaling to the virtual machine that the thread is ready to be unmounted and mounted there. Okay, so that's the problem. So you see, if I don't know if you can read what is written here, but it say notify JVMTI vthread start. So this is mounting the virtual thread. That's the problem. And this is the stop. So this is the unmount. Okay. Okay, I mentioned it ThreadLocal, and I wanted to and I anticipated that maybe we have a problem with ThreadLocal. Let me first show the happy path, let's say, what works as expected. So the reason why ThreadLocal has been introduced in Java 1.2, I think, is just to provide a thread with a context of values, so that this value, you don't need to pass around this value in the different method invocation. You bound the value to the thread, and then when the thread reaches another point of the execution, it can retrieve those value from the virtual thread. And again, you don't have to pass around this method, this value as method argument typically. Okay, so what I'm doing here is that I have a server that is serving a request, and this request may or may not be authorized. And what I do is trying to discover the principal that asked this request, and this request can have two different, and this principal can have two different set of rights. It can be an admin or it can be a guest. And of course, if it is the admin, he has the right to query the database, and otherwise it will throw this illegal argument exception. But I'm not passing the principal level from here to here. I'm setting it into the ThreadLocal, and I'm retrieving it here to use when I try to open the DB connection. Okay, so far so good. So let's try to put this thing at work, and it's actually not relevant if I use virtual thread or not. Okay, I'm using virtual thread here to demonstrate that it works. So I made two calls to this server, one with that is authorized and one that is not. and then I try to use this thing, and it works as expected. The not authorized request throws the legal argument exception, and the other, which is the authorized request, can retrieve the result from my functional database. Okay, so far so good. ThreadLocal works with both native and virtual thread, no problem, right? So yeah, but where is the problem? The problem is that the design of virtual thread, the reason why virtual thread exists, or one of the reasons, is that you can have potentially millions of them. Okay, so if you have millions of them, you will fill up the memory with the value of virtual thread, and typically virtual thread are also short-lived, so the value will stay there forever in the thread local, and you are filling this thread local data structure with waste at some point, right? So the solution of the Java architect has been this scoped value API. This is still in preview in Java 21, so you need to run this code, you need to use the ---- and I enable preview flag. Sorry, this is still the code using ThreadLocals, but you can replace the ThreadLocal with the scoped value, which is again still in preview in Java 21, but what this thing does is basically exactly the same thing that the ThreadLocal does, but just in a different way. When it calls the virtual thread, it bounds to the virtual thread the principle in a similar way to what I did with ThreadLocal. Okay, so if you want to use this pattern with virtual thread, it's better to migrate to scoped values. And of course, scoped values still work for both native and virtual thread. Okay, so we have this solution. And yeah, probably we are happy with it, and that's enough. And probably this is not enough, because I'm telling you so far only part of the story. The other part of the story, yes. Sorry? What is scoped values doing differently? Well, the scoped value, the difference is that the scoped value is lives only for the lifespan of the thread, so it doesn't remain in the thread local forever, and the other nice thing, which is questionable, is that this thing is immutable. So you can set a value inside the thread local and change it again and again during the life of the thread. In this case, you are launching this thread with this scope, but you cannot mutate it during the life of the thread, which is probably another nice feature. Okay, but again, this is only part of the story. There is another very, very common usage pattern for ThreadLocal, which is object pooling. Okay, and this is very common for a few reasons, because it's very easy to implement and it doesn't require a life cycle. So what this means? What you normally do with a pool is that with a pool, you acquire a resource, you use your resource, but then you have a life cycle, and you know when you, at some point, you need to release the resource, okay? This is not necessary if you have a ThreadLocal based object pooling, because you get the resource from the ThreadLocal, but the resource remains in the ThreadLocal, but everything is thread safe, because you are the only thread taking that resource from the ThreadLocal at that point. Okay, so you don't have to put the resource back in the ThreadLocal. The resource is still there. Okay, so if the executors will launch another task on the same thread later, it can reuse that same resource in a safe way. So this is why the ThreadLocal also are often used as an object pooling, okay? And unfortunately, this thing the scoped values is not a solution for this usage pattern at all, of course, and this pattern plays extremely bad with virtual thread. I also have an example for this. What I'm doing here, which is something quite typical, I have an expensive resources to be created. Now, in this case, for instance, when this resource is created, it is allocating lots of memory. And what I do here is that I have an executor made of 8 threads. So if I run this task 500 times, so what happens is that you have an executor made of 8 native threads. So when the first 8 thread wants to create wants to use that expansive resource, the resource is not in the thread local, but then they create it. And when a task reuses the same thread taken from that executor, then it will find the expensive resource already in the thread local and can reuse it. Okay, so let's see the difference. The first run that I'm doing with this thing is using native thread, but not using this pooling solution at all. So each of these 500 tasks will have to create this expensive resource on their own. Okay. And let's see what happens. Sorry. It takes a few seconds, of course, because again, all these 500 tasks needs to create 500 expensive resources to use it. Okay, and yes, as you can see, it takes 10, almost 11 seconds. Okay, now let's try to enable the pooling. I enabled the pooling, meaning that I'm using this pooling based on a thread local, which contains the expensive resource. And this means that I will not create this expensive resource 500 times this time, but also 8 times, because the subsequent task will find the resource in the thread local pool. Let's see what happens now. And yeah, I'm using the thread local as a pool, and this time, instead of taking almost 11 seconds, it took half a second, of course, right? Okay, so far so good. But what happens when you switch to virtual thread? The problem is that with virtual thread, you have 500 different threads. That's the point of virtual thread. You are not reusing stuff. You are not reusing native thread from an executor because they are scarce resources. The point of virtual thread is that you are free to use to create them just because they are a cheap resource. But by doing so, you are losing the thread local pool becomes totally useless, because every single virtual thread will have to create again this 500 expensive resource and take from the pool, and nobody can reuse it. Okay, so this is the problem with thread local based pooling. Okay, of course, well, not of course, but in reality, there is a very bad solution that you cannot use. And nobody can use in reality, but in the internals of the JVM, there is this thing. If you read, the name is called the carrier thread local, which does exactly what you expect. Now, the key of the thread local for a virtual thread is not longer the virtual thread itself, but it's the carrier thread. Okay. So if you try to run again this thing with virtual thread by using this specific thread local, now it is almost as fast as before. Let's try to give this a run. Okay, less than 1 second, 600 milliseconds. You see, so in reality there is a solution, but you don't want to use it. Why? Well, first of all, you cannot. I'm using it just because I'm cheating and I'm opening all the module for reflection. It's something that, of course, you don't want to do in production. But the problem here is that when a virtual thread is unmounted, then it can be subsequently mounted on a different carrier. So when this happens, it is not taking that same resources that it was using before it was unmounted. So that's the problem here. So that's the reason why you cannot use this thing. It's used internally by the Java virtual machine in some places, but not something that you can use. Okay, so we need a different solution for this. And by the way, this is not a problem that it's not really so important or that I'm making up, or it's a problem made in the void, made up for this presentation. Actually, for instance, Jackson, the Jackson library has this problem. I believe everybody here uses Jackson, right? Even if you don't know, be sure you are using Jackson in a way or another, okay? For sure. And Jackson does exactly this. It allocates a byte array, a memory space to do the JSON string conversation and use a pool to do this allocation. And unfortunately, this pool is based on a thread local. Okay, so my friend and colleague Francesco discovered this problem in February and reported the problem to them. And we had some discussion about how to fix it, and at some point I got tired of discussing it and I sent a pull request resolving the problem. This pull request has been merged into Jackson a couple of weeks ago actually, and this fix will be present with the next Jackson 2.16 release. So we are still waiting for the final release with this fix. So what I did here is that, okay, I'm keeping the ThreadLocal based pool for compatibility, but with this pull request, I'm giving an easy API first to use some other virtual thread friendly pool that are provided now by Jackson, and then if you want, you can plug your own pool implementation, which is very simple. You just need to implement this interface that does these two acquire and release method. Okay, and yeah, again, the difficult part of this pull request was not replacing the thread local based pool with a different pool implementation. The problem is that since they were using that thread local based pool, the management of this pool and the resource doesn't have a proper life cycle. There was no point in Jackson releasing that resource because with a thread local based pool, it was not necessary. So what I had to do was not only make it possible to plug a different pool, but also to set a fixed and real life cycle for the usage of this resource, because you need to release the resource with a proper pool. Is this clear? Okay, yes, and yeah, the bottom line of this is that if you have a problem with the open source library, stop complaining and send a pull request, of course, right? Okay. Thanks. Okay. One more issue. I wanted to. I said at the beginning of this talk that one of the problem is that one of the characteristic of the feature of virtual thread is that this carrier pool is a special fork join pool instance that is provided by the virtual machine, and you don't have any control on it. You cannot change it. Okay, but in reality, with some tricks you can, of course, and yeah, why not trying to change it and see what happens? Okay, so this time I put at work again my Game of Loom implementation. For the one who attended my talk last year, I played a lot with virtual thread with this thing. What is happening here, how the way how I'm putting virtual thread at work here is that this is a game of life board, so I'm hoping that almost everybody knows the Conway's game of life principle. But the fact here is that every cell in this board is a virtual thread, and the cell communicate through blocking channel with the neighbor. Okay, so in the Conway game of life, you need to know the state of the neighbor in order to calculate your state at the next frame, and all this communication is done through blocking channel, and this is why it's made with virtual thread to take advantage of the fact that with virtual thread you are not really blocking when you do a blocking operation. Okay, so what I did to put this at work is that I have this benchmark when I tried a different implementation, and just to be clear, yeah, I have this thing. I said that you cannot plug your carrier pool implementation, but of course, if you cheat a lot, it's possible. Let me show you how this works. Okay, I have this method that, okay, in essence, it accesses these protected things, and it allows you to set via reflection a different carrier for the virtual thread. Again, this is not something that you can do normally without doing this nested reflection, and it's not something that you may want to do. Okay, anyway, I wanted to play with different carrier carrier pool implementation. So what I did is that okay, this is actually these are the native thread. Really, these are the virtual thread with the default fork join pool. This is another implementation. I just replaced the default fork join pool with a fixed thread pool with 8 executor. And this is another thing that I attempted to do since I wanted to since I want to avoid the fact that a virtual thread can be mounted on a different carrier and thus causing a cache missings, if you think about it. Okay, I thought, okay, I want to avoid this, so I'm creating, instead of having one carrier pool with 8 thread, I have 8 different pool with one single thread. So when a virtual thread is created in one of these things, it remains on that native thread forever. Okay, because the carrier pool is made by only one thread. So okay, these things are just experiment, are very naive, and indeed the result is clear. I mean, here this time the score is the number of frame that I can calculate in a second. So the higher is better, of course. And of course, the fork join, the default fork join implementation outperforms all my stupid experiment. And that's nice, okay? But in reality, okay, so the carrier, the default carrier pool, it's doing pretty well, so why you may want to replace this? And actually, it turned out that in Quarkus, for instance, we may have a very interesting usage pattern. So if you know something about Quarkus, it is based on an event loop. What happens on the event loop is that you never block the event loop, right? You know. So when you perform a blocking operation, that blocking operation waits on a different thread, so you don't block the event loop, and then a second request can be served. And then when the one of the blocking operation is completed, it can restore the work on the event loop without blocking it. And if you think about it, this is exactly the same thing that happens with virtual thread. Okay, so a reactive event loop and a virtual thread machinery are modeling as exactly the same thing. Okay. And we have this annotation. We are still start supporting virtual thread in Quarkus, and we have this very nice annotation at run on virtual thread. So if you annotate a method, typically the method serving a REST endpoint with that annotation at run on virtual thread, the thread serving that request will be a virtual thread, okay? But the fact is that if this virtual thread is doing an operation that, for instance, is querying a database, then you have to pass this request to the event loop, and then the event loop will query the database. So what happens at the moment in Quarkus if you do this is that if you have a thread switch from the carrier thread to the event loop thread to do the request, and you have a second thread switch for the response. Okay, so our idea was, okay, wouldn't it be cool if the carrier thread and the event loop will be the same pool? So in this way we can avoid this double thread switch for each and every invocation, right? Because they are exactly the same pool, the same thing. So our idea is, let's take the event loop and plug it as the carrier thread pool inside Loom. Okay, and in reality, yeah, the API that I was showing you before, in reality, it was a public API till the end of 2 years ago, till the end of 2021, and then they removed it. And yes, they removed it because it was not a good idea, and we found it was not a good idea in the probably hardest possible way, right? Let me show you why this is not a good idea. So, okay, I'm doing here what I said, okay? I have this event loop, which is a single thread, a single native thread, and I'm using this event loop as the carrier of the virtual thread factory with the trick that I showed before, okay? So in this case, this event loop is also the carrier thread, okay? And here what I'm doing is that inside the event loop, I'm creating a virtual thread because now this event loop is also the carrier thread. I'm creating a virtual thread that tries to acquire a lock. And then in the native thread, I also try to acquire the same lock. Okay? So what happens here is that the main thread acquires this lock first, and then it makes it signals to both this thread with this completable future that the lock is acquired. Then it does a busy wait to make sure that both these two threads basically arrives here. Both these two threads are asking for the lock. There is one single lock. This is important. So, and then it unlocks. Okay, when the main thread unlocks, what happens is that you have two threads trying to acquire the lock. And normally what happens is that one of the two should acquire the lock, do the work, and then give the room also for the other thread to run, right? In reality, what happens if you try to run this thing? Sorry, I'm still running the old thing. If you try to run this thing, the main thread acquires the lock, then it awaits for the virtual native thread to acquire that lock. It liberates the lock, and both the virtual thread, and we have a deadlock basically. Both the virtual thread and the native thread are blocked here, and they never reach this point. Okay? So what happens here is that I'm creating a deadlock with one single lock, right? Which is quite surprising if you think about it. Because normally, to create a deadlock, you need at least two locks. You have one thread required lock, owning lock 1, and the thread 2 owns lock 2. And then the thread also asks for the lock 1, and the thread 1 asks for lock 2, and you have the two threads waiting for each other, and you have a deadlock. But normally you need at least two locks to generate a deadlock. Here I'm creating a deadlock with one single lock. And just to be clear, what is happening is that I have this situation, I have the event loop that is also the carrier thread, and then I create a virtual thread there, and then I execute both the same method in both threads, trying to acquire the lock. So they wait for the main, with that computable future, they wait for the main to acquire the lock, the main acquire the lock, signal to the other two threads that is completed, that it does that busy way to be sure that both has asked the lock, and at this point, the main thread liberates the lock, does the unlock, but none of the two threads can make any progress at this point. Why? Because the carrier is waiting for the virtual thread to acquire the lock, and the virtual thread may want to acquire the lock, but cannot make any progress because its own carrier is blocked, waiting for the virtual thread itself that is acquiring the lock. Is that clear? I know, yeah. It takes some time to. Well, you can imagine how hard it has been to understand what was going on when we experienced this thing with Quarkus, right? Because we naively tried to do this thing with Quarkus, and at some point we started having some weird deadlock, and yeah, okay, and my colleagues understood what was going on, but I wanted to recreate the same situation in an artificial way, just to be sure that to take the essence of the problem. And yeah, I didn't find an easier way to recreate the situation. I hope it's easy, understandable enough, but the problem is that it happens in reality, and you cannot do anything about this. And this is why I believe at some point the JDK architect realized the problem and closed that API that was available before. Okay, so yeah, again, this was not an introductory talk on virtual thread, but I played a lot with this technology in the latest month, and I wanted to bring you my experience to check how you can push this thing, and also to learn something about this new technology, right? So my conclusion are that yes, the usual virtual threads are not faster thread. They have specific characteristics. They don't consume resource when they block. They are not drop-in replacement for native threads, so you don't take all native thread in your application and replace them with virtual thread. This is not a good idea. And they are usually not a good fit for a CPU-bound task. And the things that they do really, really well is waiting without wasting any machine resource. Okay, and that's the thing. And by the way, regarding the story, we were asking to reopen that API, and we realized it was not a good idea. So the other bottom line of this story is that beware of what you're asking, because probably it's not what you want. Okay. And that's all I have. As I said, I'm just playing with the stuff. The Quarkus team is doing some more serious work on this. And if you are interested in knowing how Quarkus is supporting virtual thread, you can check this set of blogs that is mostly maintained by my colleague Clement Escoffier. And that's all I have. Thank you. Do you have question? Yes?
What are the differences from Kotlin coroutines?
That's a very short question that would deserve a very, very long answer. So the question is, what's the difference with what Kotlin does? Do you know the red-blue functions problem? No. What Kotlin does is coloring the function, okay? When you say suspend fun, you are saying that function has a different color. Look for this problem online. When you the suspended function and the function that are not suspended are you can think about them as two functions with two different colors, and you cannot mix them up, okay? And that's the problem. You cannot call a blue function from a red one, because otherwise also that one becomes red and everything becomes red in your application. Okay? So look for red-blue function problem and you see this thing. And you don't have this problem with this approach because you are not flagging any method with this is a blocking thing, it suspend, and it will suspend the color, that will suspend the color, and so on to the end of the stack. It's figuring out on its own, okay, this is a blocking operation, I know what to do in this case, which is a totally different thing. Okay. Yeah, sorry, it's a very, it will be a very long answer, but look for that article. It's a 10-year-old article that clarifies the problem, yes. Other question, yes?
So you try to override the pool, the virtual carrier pool, by
Yes.
the event loop pool. But have you tried the other way around to use the carrier pool in the event loop pool? You might have the same problem, but I'm wondering if
I believe, okay, so the question is, I tried to use the event loop as the carrier pool, why you are not doing the opposite? First of all, this not an experiment that we did in the void, it's something that we were attempting on Quarkus, and in that case, the event loop is the net event loop, and you cannot put there whatever you want. And second, you don't have access to it. You don't have access to the carrier pool. You don't have a reference. You cannot say, this is the carrier pool, I can use this for something else. It's private for virtual thread and virtual thread only, and you are totally abstracted away from it. That's the problem.
makes sense.
Yeah.
Anyway, it's two different scheduling.
Yeah.
It's that is scheduling versus the forejoin scheduling.
Yep. Okay, I think that my time is up. I will be around till Friday, and if you want to discuss this and whatever you want, please feel free to get in touch. Thank you.